so. Negatively charged. UV light on it. Yeah? Okay. Now, this experiment was done about 100 years ago as well. And this caused a really bad problem. And I'll explain you why. Now, I hope I have enough. Yeah, got enough paper. Now, I'll give you all the paper. And why is because everybody thought that light was a wave. Until this experiment was done. And we're going to look into that in this presentation. And what is going to happen is we're first going to look at the waves and explore them a bit. And well, then we're going to now all get your pen or pencil, whatever you want to draw with. Yes. Okay, I think these are two papers. Sorry? Well, if we have time for that, we'll see. Now, I all want you to draw a wave. We discussed wave already. You have 10 seconds, don't start yet, okay? Now, draw a wave. 3, 2, 1, go. 7, hurry up, 8, 9, long last second, hurry up, 10. Okay, stop. All pencils from. Okay. Now, Eva, show me your drawing. Okay. Doreen, also show me your drawing. Odette, show me your drawing. Nanke, show me your drawing. Now, I have the last one here. Show the drawing to the class. Yes, you.
Oh, you see, it's not like this.
Okay. Now, we saw a few drawings, and I think what the rest of us draw is a bit similar. Can someone describe this shape for me, Mirta? What have you drawn?
Waves, like
A wave. Yeah.
forms.
Okay. Now, probably something like this. Yeah. I mean, I think you can agree that that is a wave. Now we have seen the shape of a wave. So we're going to do our next experiment. We're going to combine two waves. I have two tuning forks over here, and I'll let you hear they are exactly the same. Now listen carefully. And you know this effect, I think? Yeah? Now, what I'm going to do is I'm going to make this tuning fork a tiny little bit lower. It will sound, you know, just a tiny bit. Okay. Now, listen very carefully, and tell me what you hear.
Oh, it's like the same. It's like from left to right, different.
Sounds like.
Okay, one more.
What is it?
Now, how can we explain this? We have two tuning forks. That's more than one. How can it get silent? Right? We have two, so it should get only louder. Why does it do this? You heard loud, soft, loud, soft, loud, soft.
Like that.
Why? We have two, right? So it should only get louder.
Physics.
Yeah, call it back. No, so I have combined. Okay, so this is the other wave. Go back. This was only this one. This is the normal, or this is this one, and then we have one. No, hang on. Yeah, this is the long one, so this will be. Let's see, this one, and then we have a shorter one. Now let's say that these are these two tuning forks. We have a wave that has a slightly different frequency. Does anybody remember frequency from the start of the year? Okay. Now what we see is those waves meet at different points, and this continues because one wave is a bit shorter than the other. No, it's not working. Okay, don't look.
I'm not looking.
I have this beautiful program, and let's say this is one wave and we have another wave. Now these waves are going to meet, and there are different points where they can meet, and together those two waves will combine and they make a new wave with who is a bit different. Now let's pick out 2 points at which they meet. I hope it works, it sometimes blanks it out. That's we'll have to get it wrong. Okay, go. And stop. Now, this is 1 point. If you go back to the PowerPoint, I think it's this one. No, it's not that one. That wasn't the idea. Now, here you also see this position over here, and we can say that that one is similar to the one over here. Now, has anybody got any idea what would happen with the sun if we combine those two waves at this position? What will happen if we combine them? Okay, think for a bit. Yeah? Okay, Lisette.
They like cancel each other out and just do it like softer.
Shall we have a look? You were quite right. What happens is, as these waves combine at this position, they will cancel each other out. And you see, well, I didn't place it perfectly, but you see an almost flat line, which indicates. And we have another position, which is over here. Now, these two waves are exactly at the same position, and if we have looked in the presentation, we also have this position, and it also shows, of course, in the applet. Now, what would happen? Danielle?
It's getting extra soft or harder, louder.
Extra softer and louder. Who says it will get softer in this position? Put
No,
your
I
hand
mean
up.
that plays soft and that plays louder, maybe?
Who thinks this will be louder? Yeah? Shall we have a look?
That's what I meant. There.
Now, we did this experiment.
Oh wait, it works different. I
And
feel like it's
now, if we look at this pattern, what do you see? If this were those two waves, you see points at which they are like this, and points at which they are like this.
Yes.
Clear?
Because the waves change, then it becomes soft and then harder, and then it comes with each other, against each other again, and then it becomes harder again.
Okay. Now, so what have we learned? Waves, you can add up waves, but depending on which position the wave has, it might get louder or softer. Yeah? Do you sort of see why this happens now? Yeah? Okay. So that's the first important thing about waves. Now. Oh no, we should do another experiment. Yeah, okay. We're going to do another experiment first, which is one with 2 loudspeakers. I'm going to set that up. And I want you to all stand up and go stand in a line like this, all over here and one line behind it. Yeah? So stand like this, one line over here and one line over here. Line yourselves up so that you have a bit of space in the ground. You don't have to walk on marathon, but a bit of space. Go there. Okay? Give it a red view, eh? Like this? No, I'd like a line like this. So, yeah, for example, Slash stands like this, then Lisette stands like this, and yeah, so line up. Okay.
Hey,
Ga ik vooraan staan.
Oh, they're too nice. Now, does anybody remember this device?
Can we face that way?
It doesn't matter which. I've got a bit of a cable that's on.
Loudspeaker. One face this way, you said this? Yeah.
Okay. Now, I have a constant frequency, 2 loudspeakers, so it's not the difference as we saw over here, that's not applicable because the sound is exactly the same. I can show you that, but this one, and you hear it. So this speaker produces exactly the same sound as this speaker. Yeah? Okay. Now, I know this is a sound you're very sensible for, so I'll be a bit kind to you. Now, I'm going to turn it on, and what I want you to do is, if you stand like this, doesn't matter, close the ear, not facing the loudspeakers. Not facing the loudspeakers.
Not facing.
Not facing the other side of the loudspeakers. And I'm going to turn up the volume, and I want you to move down a little bit forward and back. Okay? Now, there we go. Okay. Can anybody describe what they heard? Yeah, Meerte?
It sounds getting harder and softer.
What did you hear, Robert?
Sound getting louder.
No.
Only louder. What did you hear?
Louder
Mr.
and
Dewey?
softer.
Kind of
Wait.
wave, yes.
Okay. Now, I've got a little applet going on. Again, applets doesn't work. A little simulation. And this handles this perfectly well. It's from this point on. Anybody who can already tell me how this works? because otherwise I don't know.
I don't even know what it is. So.
Yeah.
Does anybody have an idea?
Of what?
Quantum.
Yeah?
Well, the waves go moving through the air, and if you move your head, then you hear different parts of the wave.
Okay.
Maybe.
Good suggestion. Anyone else?
That's a pretty smart answer.
Maybe
No?
Okay.
Okay, now I'm going to show you. We've got a wave going on here. This is the same idea. It's in water, but the water wave is equal to a sound wave. Now, what do you see here already? What do you observe?
Blank space.
A blank space, yeah?
Yeah, there's a space where there's like, blank space between the sound.
No way.
Okay.
They divide. And the waves become bigger.
The waves become bigger.
They can only go straight. They
And
can't.
they divide in three.
That's
Four.
5 straight lines. No, bended. It has to be in space.
Now, I'm going to just put this up, and I want someone else to explain me this. Okay, we'll start with this one.
I don't get it. What's the fish getting in there?
Yeah, first suggestion.
Two waves coming together at one point.
Yeah?
No, that the waves, when you're standing near the waves, you come to you and then you have different parts from different waves. So you hear dips.
Come on, come on. We've got physics teacher number, what is it, 5 over here, because that is indeed the very right answer. Now, if we look, yeah, please applaud. Now, what we see happen over here is we have two waves, and they meet each other at certain points. At this point, you can see they are exactly opposite of each other. Now, what does this mean?
It cancels out. So.
It cancels out, good. Now I can also show you this point.
Oh,
Oh,
that's
when they
there.
are-
That's really loud because they are the same.
And it's getting louder and softer.
Yeah, if you do this, it's softer and louder.
Now, this is very special, right? Because we have again two loudspeakers at a party. You think, well, that's always double the sound, and then this happens. Well, it won't be with it because music is too messy, but with a constant tone. And then this happens. You get loud, soft, loud, soft. Isn't that amazing? Amazing. Yes. Okay. Now, what did I tell you in the beginning? Everybody thought light was.
A wave.
So, can we do this with light as well?
Yes.
No.
No.
No, you can't like make a place fire or dark.
No.
Just put an object in front.
Can we try
And
it?
it's dark.
Is anyone curious?
Yes.
Okay. Now, I've got a very dangerous appliance over here. It's called a laser. And I don't know if it works out of the box because sometimes they take out the batteries for obvious reasons. I don't think this is a laser. Now, please close your eyes all. Yeah. Okay, it doesn't work yet. Okay. Okay. Now, it's working. This is, I don't think you can buy this legally. I don't know how legally, how a teacher got it, or whoever got it. But, we're going to do three. Okay? Now, Because,
Can we all sit again?
yeah, you can sit if you want to. Or if you want to stand, you can also stand now. Sorry, I didn't tell you to sit again. There. Now, Now what I have here, I'll show it round, is a platelet with two little slits. Yeah, can you see that? This, exactly this. And we'll make the laser go through that. Now what this will do is it will split up the light into two individual sources. Just like that one. And what you would expect, maybe, according to what you see, is like two little slits over here. Yeah? Why not? One line. Okay, so we've got some different theories going on. Now I have to be careful because this is quite a dangerous appliance. And I don't want any blindness on my... There we go. Okay, all be careful. Oh, there we go. All be careful for reflections. Now, okay. I'll make it go through the two narrow slits. And what we will see in the cupboard. Okay, be careful for your eyes. And now, I want you all to come stand close over here. Okay, please don't interfere with the laser because it might reflect on anything. Okay. Now, please. Okay, can everyone see this? Okay. Please, Anne, tell me what's happened here.
It has become wider, or?
Yeah, it has become wider. What do you see if you look carefully? We have a very bright spot over here, and we have a piece of nothing over here. We have a bright spot over here, a piece of nothing over here. If I shut off the light. So, how is this possible? Okay, we've got things we already have, correct.
Maybe there are two rays coming in, they cancel each other out, so
I'm not sure if it gets clearer if I move it a bit more, it won't improve it. Now, something fades. Now, can we relate this to this?
yes.
So this is a bit like water or sound, right? Like it gets light less bright because otherwise it overheats. So we'll take it out anyway now. So what we saw a similar thing happening. You may sit again, of course. Okay, and now we were discovering what now if we've seen all this, if I ask you what is light, what do you say?
Rays.
Okay, so are you? I didn't want that.
Question.
So are you convinced?
Yes.
Vera?
But why are, when you look at the sun, there are no black spots?
Because the sun is only one light source. If you would have two suns in our universe, two next to each other, what will happen?
You will get
Black spots.
Black spots.
It's so weird, you know.
No, it's weird.
It's really odd.
Rick,
With the laser, where was the second ray coming from?
I was splitting this laser up into two small
Oh,
small strips, and you can see that this will create a new source and the other one will create a new source. So that's what happened. Bart?
But if you have the sun
Mhm.
and you would put something like a big screen like that to slits, would it also create dark spots in the earth?
That's so odd.
Let's do it. Okay, now, not everybody was convinced about this, and this has to do again with this experiment, what we just did. Now, this man wasn't a joke. He was Albert Einstein, and he didn't quite agree on this theory. And this was his evidence, and we'll talk about that in a bit. I have to look at my presentation, what we're doing. Okay, so Einstein wasn't convinced, but you just told me all your way, and you're like, well, 25, 24 plus 2, so 26 people. Are you all dumb, or is Einstein really smart? Now, why wasn't Einstein convinced? Convinced for later. To look into that, we're going to build an atom. Now, let's just make a simple one. This is a plate of zinc, but I don't have enough building blocks to make a zinc atom. So, there we go. So we'll make it. Now, this is important, the net charge. What do we see after we've done this? 0. Now, I just charged this negatively. I told you about that. So what we did is we added an electron. Yeah, we know we can add electrons to an atom. We learned about that. So now we have this atom, and it has a net charge of -1. You understand?
Yes.
Yeah? Okay, now, if we want to get it to 0 to this position again, what do we need? More protons, or less electrons. So we need to rip off an electron. Now, this doesn't happen just suddenly. You need energy for that. I mean, this thing wasn't discharging just straight away, was it? No. And you need a lot of energy to do that. Now we need to look into the wave. Vera?
Does the light make the waves, and then the waves give the energy to
Yeah.
the
To the electron. And the electron gets so much energy it wants to fly off. Now we need to look into the wave to see what in a wave determines the energy, because we need a lot of it, so we want to add more. Now we see it succeed with this. How did that come? We have UV light, ultraviolet light. We talked about this a bit, it was last year, it was with Mr. Rossen. He told you about all the different sort of lights, and it has to do with frequency. Does anybody remember that? Okay, so at the one end we have infrared light, which is used in the electric heaters. You sometimes have, we have ultraviolet light, which is on the other side of it. Now the energy is determined by the amplitude and the frequency. The frequency, the vibration per second, which is how fast it goes like that, determines a sort of wave. For example, red versus blue light. Red light has a lower frequency than blue light. Now, if we amp up the frequency, we have enough energy to rip off an electron. We just saw that, right? Now what does this say?
You don't have the
amplitude.
amplitude.
This is the amplitude.
Oh.
Remember with the sound, really loud waves, the difference between this and this.
No move it.
Low amplitude, high amplitude. Now, what do you think this laser is? Is this a low or high amplitude? High. This is a really, really strong laser. So this has a lot of energy. I think you can agree it can burn your eye, so probably it has a lot of energy.
Yes.
Yes. Now, we could do it by increasing the frequency, and if we take into account the amplitude of this laser, we should easily manage to rip off that electron. So you try it.
Yes.
Okay, let's do it.
And then you will shine with the
Now I can't, have to be careful with this one. I'll shine on it, and you have to watch what happens. Yeah? Okay, there we go.
nothing.
Stay for a bit.
Boom.
Oh no!
Not enough light. Not enough energy.
Not enough energy. Well, I just explained to you that if we did the calculation according to the waves, I'm not going to give you all the formulas, we would have easily enough energy. And this wasn't that bright, wasn't it? Was it? I mean, you could see it, but it wasn't incredibly bright. It did have a high frequency. This is very bright. This is, I think, the brightest source of light you can get quite easily. Yeah?
Maybe like the kind of wave is different than that kind of wave, so that is why that does move and it doesn't move with the laser.
Well, and this orange red light, and the other one was white bluish, so maybe.
Okay, I'll have to move on because otherwise we can't do the whole presentation. Now, Einstein proposed that light was a particle. Please draw a particle for me. I want to see what a particle looks like. You get 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Please all stop drawing. Now show me your. Yeah, just hold it up. Everyone hold it up. Okay. Look at each other's particles. Okay. Okay. Take it down again. I have a question. I saw you all with rounds and bubbles and, well, sort of things that had meant to be rounds, but it wasn't quite. Why did no one draw a square? Why not? We always show them with a. So we can say a particle is sort of a little ball. Now, why did Einstein think that light was a particle? Okay, if light is a particle, then the more particles, the higher the intensity. So we can say that this are a lot of particles. It's particles flying in the air with many of them, billions.
Where do those particles come from?
They come from over here,
They,
from the laser. I'm not going to into how you create particles, it's a bit too complicated, okay? For now, sorry. We can do it in another lesson. Yeah?
So when the particles have wouldn't you then be able to like catch them in a jar and have the jar of light particles?
Well, if you can catch them, but light always goes with the speed of light and nothing else goes with the speed of light. So if you want to close the lid of the jar,
Well, if
you know, you're never
light
fast
that way,
enough.
then you-
Oh, you can put light in a container, but to see light, you has to reach your eyes, so the particle has to hit your eyes. Now, intensity is thus the number of particles. Individual particles have their own level of energy determined by the frequency. So each little particle has a lot of energy or very little energy. Yeah? We call this frequency. You can also see this vibration. So infrared light has less energetic particles than UV light. Now, So each of those particles have their own quantity of light. This is where the name quantum mechanics comes from. Light is quantized. It's in different particles instead of just a wave. And Einstein called this particle a photon. You may have ever heard of it, I don't know. Now what does this mean? Okay, see, frequency is the energy is frequency of an individual particle. Now, I don't know what slide I have after. Yeah. I think we're gonna make it, but we might need 5 extra minutes in break. Do you want to sacrifice your break?
Yes.
Okay. I have this applet. Just to load for a bit, and I'll explain you why this experiment proves that light must be a particle. Now, to understand that, you have to look into the atom. We need to rip off one electron. How can we do this with a lot of energy? If energy is contained in one tiny particle, then the one tiny particle has to have enough energy to rip off that electron. Because only one particle will hit the electron at a time. These particles are really small and the electron is also really small, so most of them will fly past. But I have to rip off one electron at a time. If you have waves, you could count them up and you get brighter and darker spots. So you can just amp up the amplitude and you get more energy. It doesn't work like that with a particle. It has to have its own frequency. Now what does this mean? This means that in this lamp you might not have as many particles, but you have much more energetic particles. And you can have many particles, but if the particle in itself doesn't have enough energy, you can shoot as many particles at it as you want, but it's not going to cut it. It's just like thinking that you can knock over this school by throwing water balloons at it. You know, you can throw 1 million water balloons at it after each other. I'm telling you, the school won't collapse. And that's a bit like this. Now, if we look at this, I'll make it infrared light. Now, I have an intensity here. Slide it up. You can even make it a bit red. Like this. Okay, so this is 50% intensity. Nothing happens. Yes. Now, if we increase the intensity, with a wave, what would we get? More energy. Why? Because the wave gets bigger. What will happen if we have a particle? We'll get more
Particles.
More particles. Will the particle get more powerful?
No.
Okay. So what can we see electrons flying past here?
No.
Okay, let's see. Quite right. Now if I turn into a UV light,
Then you can.
I have
Yay.
now we have zero like this. Okay. Now we have no intensity, which means no particles flying from this, so no electrons will be released. But if we amp up intensity, we can see that these particles will fly up, and this thing will discharge. So that's what happens in here. We have a lot of, well, not that many, but we have very energetic particles, and that's going to make sure that the electron will fly off. Okay, I know this is very complicated stuff. Is this a bit understandable? Yeah?
I don't understand the part where you said that with red light, you don't have any electrons, it's like why. I don't understand.
Okay, that is because you need a certain amount of energy to let the electron fly off. Yeah? And if that energy isn't contained in this one particle, then it's not going to happen. Now, if it's infrared, this particle doesn't have a lot of energy. So you can have many of them, but it will never happen. Yes?
But then indeed the electron has the energy to
The electron has the energy Well, the electron means negative charge. Electron is a negative particle. So if this is negative, we need to rip off the electron, and if we do, it gets well neutral, or if we apply more energy, positive. Now I'm going to wrap it up because I see someone really not that. Okay. So what is the truth? You tell me. Now we'll end this presentation in a very fun way. You may stand up again, and here we go. This is a map of our classroom. I'm this currently. Well, not exactly, but you get the idea. So if we have if you think that light is a particle, go over there. If you think it's neither, because I mean we saw the interference, the light getting dimmer and not dimmer. With particles, would that be possible? That's another question. So if you don't know, you can stand here. If you think, well, I just saw this awesome pattern over here, I'm definite that light must be a wave. You stand over there.
Let's go to magic.
Particle, magic, or neither. And over here we have the wave. Please all take your position.
Magic slash particle. One step in.
Magic particle. Yeah, okay. Okay, and we see some really interesting things. Matthijs, can you explain why you think light is a particle?
Yeah, well,
Is it because of what I just told you? What I
Yes.
showed you with it? Shall we do it one more time? Then it heats up. While you explain, go.
yeah, just as you told, I don't think a wave can knock off an electron because it is not, well,
Powerful enough.
yeah,
Okay, very good.
not.
Nanke, why is it a wave?
Because of the laser light, and
Laser light.
if it were particles, it probably wouldn't have
No. Because, I mean, a particle doesn't do that. And we've got many people in neither. You're surely not sure. Is anyone willing to explain why? Yeah, he said.
Well, I have the feeling that both wave and particle prove each other wrong, so that wave says like, well, it cannot really be a particle because of this, and particle says it cannot be a wave. So then it must be logical.
Look at screen, so that has to be right.
I think it must be neither.
Okay. Now you are actually giving the explanation that most scientists give for this. They say we don't know. They have models to be able to calculate something with it. But if you ask them to explain what light is to a 6-year-old, can you do that?
Magic.
No, not really.
Yeah.
Now, what do I think? I'm not sure if you're interested, but I think it's really cool to see that we take examples of the world we can see. You draw the ball and the wave, we can see that in water, to explain the smallest things on Earth that we can imagine. Now, so we try to take something we can see to explain something we can't see. Now, this causes this sort of problems, and I think it's really interesting because, well, we're not sure what happens. Well, not actually really, but you know, they can cooperate with it, and I think it's fine. Now, last time this experiment, watch the electroscope. You now know what happens, so that's also fun. And watch it. Now, this was the end of my presentation. Okay, one more question.
Do you think it's a wave or it's particle or neither?
I think it's neither. I will be in the middle category. It's we use sometimes we say it's a particle, sometimes we say it's a wave. But I'd say it's something completely different, and I don't think we're quite sure yet what it is. And we'll probably figure it out one day, but at this point we don't know yet. Okay.
Because when we did, this is what we normally do in the 6th form, and then we take several weeks, and after did it in just one lesson. So once more, come to the first
Why was the line red?
Okay, I forgot to ask about the two suns. The two suns. Who said if there were two suns, would there be black spots? Who asked that?
Oh yes, Jens, you did. Oh.
Okay, now here, let's applaud Vera for a very I'll make it meeting. Thanks very much for staying on.